Hi, so today I'm going to talk about dynamic programming. Dynamic programming, although it says programming in its name, is more of a discrete mathematics problem solving technique. So, in dynamic programming, what we do is instead of using regular recursion algorithms or loops to solve the problem, what we do is we solve the bigger problem by breaking it down into smaller sub problems and save all the answers to the possible solutions and connect all of that and try to get the bigger problem answer. So for this to work, the problem that we solve using dynamic programming needs to have two characteristics. That is, it needs to have optimal substructure. Substructure means the possibility to break down the problem into very small subproblems and get the answers to all their smaller subproblems and connect all of that together to get the bigger problem. And the next characteristic is it needs to have overlapping subproblems. That means uh, when you're regularly trying to solve this using recursion, the same subproblem has got to be found throughout the algorithm many times. So what we do is we cache each of these subproblems when we solve it and save its answer. So the next time we see it, we will already have the answer to it. So for the caching, we usually use two techniques. It's called memoization and tabulation. You can research into that if you want to dive deep into dynamic programming. So, for example, I'll start with a very famous problem that we solve. That's the Fibonacci problem. The Fibonacci problem is if you got an array like a 0, 1, every fib number, the next number in the list is the sum of the earlier two. So the third fib number is 1. The fourth fib number is the sum of these two, 2. Then it's going to be 3, 5, 8, and so on. So usually what we solve this is using recursion. As you think, what we do is we uh, define the function fib n as fib n minus 1 plus fib n minus 2, and we set the base cases as fib 0 equal 0 and fib 1 equal 1. And then we call fib, if you want to solve fib 5, what we do is we calculate fib 5 equals fib 4 plus 3. Then we go here 3 plus 2, 2 plus 1, and 2 is going to be 1 plus 0, and since these are the base cases, we add them here. And this is the whole recursive tree that happens when we are using recursion. But as you can see, we have solved the same problem multiple times. Fib 3 is calculated 2 times, fib 2 is calculated 3 times, fib for 2 just to calculate fib 5. But when we are using dynamic programming, but as I told you earlier, we are going to cache this fib 2, fib 3, and fib 4 each time we solve it. So the next time we come to it, we will not solve by adding these two, we will just look from it. And when you come here, we won't have, this entire tree will be eliminated because we can just look it up from here. Then earlier the problem had a time complexity of the big O of 2 to the power n. So by caching these subproblem answers, what we've effectively done is we've been able to reduce this down to a big O of almost n. So when we're using dynamic programming, what we do is we try to calculate fib 5, that means fib 4 plus 3. We don't know either of those when we start out, so we first calculate fib 4. We don't know 3 plus 2, we calculate fib3. We don't know fib2, so we calculate fib2, which is initialized as the base cases. Okay, now we know fib2. Then we go up to here, fib3. Okay, we know fib3. We can recall fib2 from the memoization array. So we can find these two without going down a whole tree. Now when we go to fib4, fib3 is already found here and fib2 is found here. We can just add these two values and get fib4. And when we come here, fib3 is found here, fib4 is found here, and fib5 can be calculated very easily. So that's a simple problem that can be solved using dynamic programming, but we can even go down to more complex problems such as the um, 0-1 knapsack problem. The 0-1 knapsack problem is, assume you have a bag that can hold 5 kilograms, okay? And you have a bunch of items that you can pick that each has values. So your task is to pick as most items as you can so that you won't overflow the bag, but still you have the maximum value. So there has to be a proper answer to this. So it cannot be like a random answer or an ambiguous answer. So what we usually do is, if we are doing this naively, we will find all the combinations of the values, and out of those combinations we throw out the values that has the total weight that's more than 5 kilograms, and out of the remaining values we get the maximum value. So this will be heavily time consuming, but using dynamic programming, what we do is we fill up a memoization table like this and fill it up using an algorithm that adheres to dynamic programming constraints. So the algorithm that we come up using dynamic programming is, for each of in this table we fill up using the two choices that we have when it comes to each item. So when you see an item, you can either put it in the bag or not put it in the bag. So these are the two options that you can take. So what we do is, if we skip this item, the value of dpiw will be the same as if we did not have that item. It'll be the same value. So we go up the table. So this is I and this is I and this is W. So if we do not choose the laptop, that means the value should be the same as a row above it because we did not choose the laptop. But if we choose the laptop, what happens is we go up a row and the weight will be reduced by the weight of the item that we're picking, but the value is going to be increased by the value of the item we're gonna pick. So if we did pick the laptop, the weight of the laptop is 3 kilograms and the value is 4. Then if we did not pick the laptop, it's going to be here, and if we did the laptop, we're going to go down to here, such as 4. So what we do is we recurse this algorithm from the top until we reach these base cases and we fill up the memoization table. So in this case, we won't recursively find all the combinations. All we do is we fill up a table that's I into W size. So the space complexity is going to be just big O of I into W, and the time complexity is going to be the same. So this is how you can use dynamic programming to calculate optimization problems in a more efficient manner. There are more techniques into this, and this gets more complex, but this is an overall brief of what dynamic programming is. So if you guys need any more clarification or help, please feel free to text me on Teams, and happy learning. Bye bye.